Alright, so now we're going to compare the graph of position with respect to time and the graph of acceleration with respect to time. We'll go on and we'll look at acceleration and velocity too. But I want to start with this one first. I want you to pause the video real quick and then compare it and contrast it. See if there's any differences you see here from here. See if there's any similarities between the two. Okay, so pause it really quick. I'll hold my breath. And just try to compare and contrast. Okay, so hopefully you pause that video so I don't have to hold my breath for too long. So, compare. Well, once again, frequency is still the same. Boom, 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 boom. They behave exactly the same. They have that same period. Bonk, 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 bonk. Okay? Cool? The other thing that's important is both of them are starting at 0. Both of them achieve 0 points at the same time. That means that when the position is at 0, which means in this motion, up and down, right at the center, when the position is equal to 0, the acceleration is equal to 0. Okay? So that means at those points, you've got a 0 position and a 0 acceleration. Okay? Cool? So those are some similarities, differences, size, amplitudes here. They can be different sizes. More than likely, expect your accelerations to be considerably smaller than your position and values. It's not always true. There are situations where this value can be considerably bigger than this value. I mean, if this omega, this natural frequency, is greater than 1, then omega squared is certainly going to be bigger than, or x times omega squared. Sorry, it should have been x max. Let me fix that real quick. That x max times omega squared should be greater than this if that omega is greater than 1. Okay? Differences. They're completely out of phase with each other. When this one reaches a maximum value, the highest point, this one reaches the lowest point. Wow, that's actually an interesting thing to think about. So as the object achieves its maximum point, it reaches its maximum height and it starts to head down, its position is in this direction. It's pointing straight up. So as it goes up, its position is this way. It's positive. It's pointing up. But it's achieved its maximum negative acceleration, which would be its minimum acceleration, down. So there's an acceleration down on the object when the position is up. Okay? When the position is down, when it's reached its lowest possible value, like that, when its position is down, its lowest possible value, its acceleration is up. It's its highest possible value. It's reached its maximum. So that's a major difference between these two. They're completely out of phase with each other. When one reaches the top, the other one reaches the bottom. Okay? And that actually is the reason why it's simple harmonic motion. When you achieve a positive x value, an x value, you're experiencing a negative acceleration, which means that the acceleration and the position are always in the opposite direction of each other, with the exception, of course, of 0. There's no real direction of 0. But everywhere else, except for on that line, the positions are positive, the acceleration is negative. They're opposed to each other. Okay? Which, if you think about it, is what it keeps moving. If it reaches its maximum, there's an acceleration to pull it in this direction. Once it's traveled beyond that equilibrium, the acceleration starts to point up and it gets bigger and bigger as it goes down. Okay? That's position versus acceleration graphs. It's really kind of interesting if you think about it. How they behave and why it's simple harmonic. Why it behaves the way it does. Okay? Now next I'm going to bring up velocity versus acceleration.